All right, so this is Chapter 2, Sections 2.1 and 2.2 for AP Chemistry, presented to you by Guy Difini. All right, so Section 2.1 is about the atomic theory of matter. So Democritus said that the material world, or matter, is made up of atoms, but then later on, Plato and Aristotle were like, Democritus was wrong. So the atomic theory kind of disappeared for a little bit. Just a definition before we get into the other stuff. An atom is the smallest representative particle of an element, and it's the almost infinitesimally small building block of matter. So the notions of atoms and atomic theory and all that stuff reemerged in Europe in the early 17th century, or in the 17th century, sorry, with John Dalton's atomic theory of matter, or atomic theory, which is based on four postulates. Each element is comprised of extremely small particles called atoms. All atoms of a given element are identical, and atoms of each element are unique to that element. Atoms of one element cannot be changed into atoms of a different element. Atoms are neither created nor destroyed in chemical reactions. And compounds are formed when atoms of more than one element combine. And a given compound always has the same relative number of kinds of atoms. So Dalton's theory explained many known laws of chemical combination at the time, like the law of constant composition, definite proportions, which is in a given compound, the relative numbers and kinds of atoms are constant, and also explained the law of conservation of mass, which is the total mass of materials present after a chemical reaction has to equal the total mass present before the reaction. And then Dalton also used his atomic theory to produce the law of definite proportions, which is if you have two elements A and B, and they combine to form more than one compound, the masses of A that can combine with a given mass of or masses of B that can combine with a given mass of A are in the ratio of small whole numbers, and you can see that in empirical formulas and stuff like that. So 2.2 is the discovery of atomic nature. So during the mid 1800s, scientists observed cathode rays when a voltage was applied to the electrode in a tube of almost empty air. So cathode rays went from the negative to the positive electrode, and rays were detected via fluorescence with certain materials. And here's kind of like a diagram that'll help illustrate the cathode ray tube and kind of what it was about and how it works. So yep. And then British scientist J.J. Thomson described cathode rays, and this is the year he lived, by the way, the 1856 to 1940. He described cathode rays as streams of negatively charged particles that we now call electrons in 1897. And an electron is a negatively charged particle, subatomic particle, found outside the atomic nucleus. And this is kind of this graphic here is an illustration of Thomson's experiment. And basically, he was able to manipulate the magnetic and electric fields to affect the path of the electrons. And this actually resulted in him figuring out the charge mass ratio of the electron. So, and that'll be important for later studies. So later on in 1909, Millikan, and these are the years that he lived, succeeded in measuring the charge of an electron by performing the following experiment, which is called his oil drop experiment. And this is a pretty important experiment to know. And then after this, he actually calculated the mass of the electron by using his experimental value for the charge and Thomson's charge to mass ratio, or Thomson's charge mass ratio. So here's kind of another graphic of his oil drop experiment. And I have these graphics here as well, and this little explanation that I wrote down here in my notes to kind of better understand this experiment, because I feel like it's pretty important to know. And yeah, sometimes it's kind of hard to wrap your brain around, especially when Googling it. So you can use this if you needed. And then Millikan's result agrees pretty well with the currently accepted value for the electron mass. So that's pretty interesting. Henry Becquerel in 1896 discovered that a compound of uranium spontaneously emits high energy radiation, and this is called radioactivity. So that's pretty cool. And then Marie and Pierre Curie ran experiments to identify and isolate the source of radioactivity in the compound at Becquerel's suggestion, and they concluded that it was uranium atoms. So those are some cool fun facts. And then Ernest Rutherford studied radioactivity further and revealed three types of radiation, those being alpha, beta, and gamma. And in 1907, Rutherford did his famous alpha particle scattering experiments, which is kind of this slide here, and this is like a graphic that kind of explains that experiment or whatever. And from his experiment, Rutherford concluded that alpha and beta rays consist of fast-moving electrically charged particles, and then beta particles are nothing more than high-speed electrons. Their negative charge, -1, means they're attracted to the positive plate, and then the alpha particles are positively charged with 2 plus and are attracted to the negative plate. And alpha particles are 74,000 times heavier than electrons, which are the beta particles. And then gamma radiation is just high energy electromagnetic radiation similar to X-rays, and it doesn't consist of particles and carries no charge. So that was just kind of his big experiment thing. All right, and then during the early 1900s, back to Thomson, he reasoned that since electrons contribute to a very small fraction of an atom's mass, they are probably responsible for a small portion of the atom's size. And he proposed his plum pudding model of the atom later on. And this is an atom that consists of a uniform positive sphere of matter in which mass is evenly distributed and in which the electrons are embedded like raisins. So it's kind of like a cookie, and like most of it's that positive sphere, which accounts for most of the mass. And you have like those little dots of electrons everywhere, like the raisins. And in 1910, back to Rutherford, he performed his alpha scattering experiment along with Ernest Martin. And he was the one, Ernest Martin, who actually observed the large angles that the particles were deflected at, while Rutherford only saw angles that were consistent with the plum pudding model. And the fact that Martin saw this disproved the plum pudding model entirely. And all this will be seen on the next slide. I have a graphic, so if this seems confusing now, I'm sorry. Rutherford explained his results by postulating the nuclear model of the atom, which is kind of a more modern version of the atom that we know today. It's the model of the atom with a very small and extremely dense nucleus containing most of the mass, which is the proton and neutrons, with the electrons outside the nucleus, like floating around. Rutherford postulated that most of the volume of an atom is empty space in which the electrons move around the nucleus. So this is his other alpha particle experiment. And if you want to read this graphic through, you can. I highly, highly, highly recommend it. It will definitely be asked about. So yeah. So, protons were discovered in 1919 by Rutherford and neutrons in 1932 by James Chadwick. And these are the years that he lived. Thus, the atom is composed of protons, neutrons, and electrons, and that's the model of the atom that we know today. And just some definitions: protons are positively charged subatomic particles found in the nucleus of atoms, and neutrons are is an electrically neutral particle found in the nucleus of an atom, and it's about the same mass as a proton. And then again, the nucleus is that very small and dense, positively charged portion of an atom. And it's composed of protons and electrons, and then most of the atom is empty space with the electrons floating around according to this model. So, some quick quiz questions to make sure that you were kind of on track. I know that was really fast, but it was a lot of information. I have to get this in a certain amount of time. So, number one, what did Democritus say about matter? Number two, what are John Dalton's four postulates of his atomic theory? Three, what's the law of definite proportions? Four, what was Millikan's notable experiment? Five, what three types of radiation did Rutherford revealed? And six, what was Thomson's contribution to the discovery of atomic nature? So let's pause this, answer those questions, and we'll go over the answers really quickly in a second. Okay, so the answer to the first one. Democritus said that the material world, or matter, is made up of atoms. And for number two, here are John Dalton's four postulates. You can read these over, check to make sure you got them right. They're just straight from the slideshow, like how we went over. Law of definite proportions, just that same definition from the slideshow. So if you want to go over this, make sure you got it right. Make sure you got that down, because I remember him asking us about this on the test. It's pretty important. Millikan's notable experiment was, again, that oil drop experiment. Make sure you kind of know how it works and like the significance of it. In addition to like all the experiments here. So three types of radiation were alpha, beta, and gamma, which were the ones that Rutherford revealed. And then Thomson's contribution to the discovery of atomic nature, his charge and mass ratio of electron, which was used later on, and his plum pudding model, which was later disproved, but was kind of, yeah, it was a stepping stone in the development of atomic nature. So that's it. This unit is kind of like, I don't know, my least favorite, because it's like a lot of history and stuff, but it's good to know. It's good to know how like it all developed. It helps you understand everything a little bit better. And I hope this helped. I know it was fast, but you can use this as a reference if you need to. So thank you.